Hello and welcome. In this video, we're going to talk about continuous functions. We're going to define what continuity is using limits, and we're going to talk about the different types of discontinuities. So our goals in this lesson, I can identify types of discontinuities, and I can determine if a function is continuous using limits. Let's go ahead and jump right in. The basic idea of continuity is really simple. The idea is a function is continuous if I can draw it without having to lift up my pencil. That's not really a very mathematical definition, but conceptually, I think you can look at something and tell if it's continuous by asking yourself, could I draw this without lifting up my pencil? Now, the formal definition has to do with limits, which is the perfect thing to mention since we have been talking about those limits. So formally, we say a function is continuous if, as x approaches any given x value, the function approaches the exact same value. Basically, what that means is a function is continuous when the limit is the same number as the value of the function. So let's write that out notationally. So notationally, we're saying f is continuous at some c value if the limit as x approaches that c value is just what we get when we plug c into the function. So we're going to come back to this definition after we really focus on what makes a function discontinuous. So if you look at these three problems on the right-hand side, all of these are functions that have areas in which they are not continuous, x values that we are not allowed to plug in. So what I want you to do is to just take a look and see if you can figure out what x values each of these functions are not continuous at, and then we'll talk through them together. All right, so hopefully you had some time to think this over. On number 1, f is not continuous when x is equal to 5, because that would make the denominator 0. On number 2, x is not continuous when x is equal to 0, because, again, that would make the denominator 0. On number 3, f is not continuous when x is equal to plus or minus 3. And what we're actually going to do now is we're going to formalize what is happening at each of these x values to create this discontinuity. So we're going to talk about what are the different types of discontinuities. So the first type of discontinuity that we're going to talk about is a hole in a graph, and we've seen this in graphs before. What that means is there's an open circle, but the function from the left and the right just keeps going. So that just doesn't exist at that one particular value. What this looks like in a function is that we have a factor in the numerator and the denominator that divides out. So here's an example. If we have x minus 3 over x plus 3x minus 3, the x minus 3's are going to divide out, and that would create a hole in the graph. What I want you to notice about the graph is if I asked you for the limit as we approach that open circle, as we approach that hole, the limit is still going to exist because what's happening to the left and what's happening to the right of the graph are the same. So even though the function is not continuous at that value, the limit still exists, and that is what it means to be removable. So a hole is a removable discontinuity because the limit still exists. A jump discontinuity is when we have two pieces of a graph and we pick up our pencil and we jump from one place to another. It's also called a step discontinuity. This often comes from piecewise functions where the function is defined to be one thing and then at a value it changes the way that it is defined. A jump discontinuity is non-removable because the limit isn't going to exist. One-sided limits will exist, but two-sided limits will not exist. Similarly, a vertical asymptote, which we know is a dotted line that our function approaches but never crosses, is also a discontinuity. That typically we see that in a value that makes the denominator equal 0. So for in this example over here, x equals negative 3 would be a vertical asymptote because the denominator would be 0, as opposed to x equals 3 would be a hole in the graph. And a vertical asymptote, the limit is not going to exist because the function is going to be approaching infinity or possibly approaching negative infinity. So both jump, also known as step, and vertical asymptotes are non-removable discontinuities because the limits do not exist. The two-sided limits don't exist. So let's look at some examples, identify the different kinds of discontinuities that we see, and then we can move on. All right, let's actually look at, I'm going to call this example A and example B. Let's actually look at example B first. Looking over the definitions that we just wrote down for the different types of discontinuities, I want you to ask yourself, what's happening when x equals 2? Now, hopefully you had time to think through that. What's happening at x equals 2 is that there's a jump discontinuity, which is non-removable. Because we're jumping, we have to jump from our paper from one place to the next. Now, if we look at example A, I want you to first identify all the places where there are discontinuities. So pause the video and write down each x value that is creating a discontinuity. So I see 4 places in the graph where we have discontinuities. One here where there's an open circle, another here where there's an open circle. I see a vertical asymptote here with this dotted line, and then I see a jump discontinuity here. So here are the 4 values that I see we have discontinuities at. For both x equals 1 and x equals -1 and x equals 2, there's a hole, which is a removable discontinuity, which means the limit would still exist at both x equals -1 and x equals +2. X equals 3 has a vertical asymptote, x equals 5 has a jump, and both of these are non-removable discontinuities. So hopefully you could look at an image and identify a discontinuity, and we're going to focus on what that looks like from a function as well. So if we're given a graph, it's usually easy to identify if something is not continuous, if we have to lift our pencil to trace what's happening. If we're given a function, it's a little harder to identify that, specifically if we're given a piecewise function. If we're given a function as we saw in the first 3 examples, we could just figure out what would make the denominator equal 0. We can now define those types of discontinuities. But if we were given a piecewise function, we can talk about continuity by looking at what's happening to the left and the right of each particular piece. So another way to define continuity is using one-sided limits. So we can say that if the limit, as we approach C, of both the left and the right side of the limits is equal, and make sure you add this, and they're equal to the value of the function when we plug in C, so this goes back to that original definition, then a function is continuous. So if we look at example 6 here, we know that this top piece, 4 minus x, that's continuous everywhere that it covers, right? That's just a line. We also know that this bottom piece, 4 minus x squared, that is continuous everywhere that the graph covers. So what we need to know is what's happening at this particular value where we're changing from that line to the quadratic. So what we're going to do is we're actually going to look at one-sided limits. So we're going to look at the limit as x approaches 1, this number, from the left, which means we're going to use this red piece, of 4 minus x. I want you to notice that the function is defined to be at that value. So this is also equal to f of 1, which is this f of c piece that's essential here. Well, we can do direct substitution here. 4 minus 1 is going to give us 3. So that's what's happening when x equals 1 on the left-hand side of the graph. On the right-hand side, so the limit as x approaches 1 from the right, on the right of 1, we're going to use this function. If we plug in 1 here, we're going to get 4 minus 1, which is also 3. So since these two things agree and the function is defined to be the same value, we can say that this function f is continuous everywhere. So I'm going to write this in kind of fancy calculus notation. I'm going to write therefore, that's what those 3 dots mean, since the limit as x approaches 1 of f of x, and you could use one-sided limits if you wanted to, is equal to f of 1. F is continuous everywhere, because 1 was the only place that we were questioning whether or not it was continuous at. We're also going to have that same question here on this next example. So I'm going to encourage you to pause the video and try and work through number 7 on your own. Use number 6 as your step-by-step guides and work through number 7 on your own. Then unpause the video and see how you did. So if we plug 1 into the top piece, and I want to see these limits when you're doing this work, if we plug 1 into the top piece, we get 2. If we plug it into the bottom piece, we get 3. Those are not the same. So this function is only continuous. Well, it's continuous everywhere except for x equals 1, and we can use interval notation to write that. So since 2 and 3 aren't the same, f is continuous everywhere but 1, so continuous on negative infinity to 1 and 1 to infinity. Let's go ahead and wrap up this video. Our goal in this video was to be able to identify different types of discontinuities, holes, which are removable, jumps and vertical asymptotes, which are not removable. And remember, removable means the limit still exists. And lastly, to determine if a function is continuous using limits, which we did in those last two examples. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.